Hi, everyone. I got like 2 highs. Hello, everyone. Awesome. That was much better. Thank you, everyone, for coming to Taming the Modern Data Center. If you're not here for Taming the Modern Data Center, you are in the wrong room. Feel free to stay. What I want to challenge everyone to do here today is kind of come into this with an open mind. So I'm going to challenge a lot of what you know about data center management, modern cloud computing, configuration management, buzzwords. So keep an open mind, and I promise you, by slide 4,768, it will all make sense. That was a joke. There's only 4,000. So who am I? I'm Seth Vargo. My internet handle is Seth Vargo. It's really original. You can find me on Twitter and GitHub. I work for a company called HashiCorp. You may not have heard of HashiCorp, but you've probably heard of many of our open source tools. So Vagrant, Packer, Surf, Consul, Terraform, those all kind of fall under our guise of what I work on every day. And we're actually going to talk about most of those here today. So everything I talk about in this talk today uses open source tooling. You can download it right now, install it on your laptop or desktop or Windows machine, and go. So we're talking about taming the modern data center, but before we get there, we have to talk about what is the modern data center, and more importantly, how did we arrive at this definition of modern data center? What's the history? Why are we in this situation? What problems were we trying to solve? So originally, and I'm talking originally like 30, 40 years ago, whenever data centers were the sizes of football fields and had a collective RAM of 256 megabytes, we had one massive server, and that's what ran, our punch card Fortran. And very quickly, those data centers evolved into smaller servers with more computing power. So we have racks and racks of servers, racks and racks of networking equipment, but it's all bare metal. Everything runs on these bare metal machines. It's very expensive to provision them and acquire them, but they're highly performant, but they're really only available to companies that can invest the capital to fund them. Well, then VMware comes along, and a few other virtualization technologies start taking place, and all of a sudden, we don't need to run on the bare metal. We can run on the virtualization layer at a performance hit, but the performance hit was worth the trade-off because we could quickly create and destroy virtualized kind of sub-machines, right? These were real machines running on real hardware, but they were virtualized. And this was kind of like a revolution in computing at the time. And then enter like the last 2.5 years, and we run containers, which are not VMs, but we run our containers on our VMs that run on bare metal in our data centers. But no data center actually looks like this, and very few organizations are running all containers, all VMs, all bare metal. In fact, it gets even more complicated whenever you start adding the external services, the SaaSes, for example. So you might be outsourcing your DNS provider, you might be outsourcing your email provider, and the communication to and from your data center, to and from your applications is becoming exponentially complex. You're using a hosted database. What happens when the network goes down? How can you secure that connection between a database that is run by an external provider and your VPC and EC2 or your brick and mortar data center? Even more so, what if you have a physical data center and a virtual data center? So you have your physical data center where you need to tightly control everything that's going on, and then you have this cloud staging environment that nobody really cares about, but we have it because the developers asked for it. And how can we link the data or not link the data between those data centers effectively? It gets even more complicated when we realize that it's a hybrid environment of all of these things. So we have our cloud data center that is running in EC2 or DigitalOcean or some type of infrastructure as a service provider, but then we have our bare metal data center that has these physical servers that we've acquired a long time ago. We've installed virtualization technologies on them so that we create VMs, and on those VMs we're running LXC or Solaris Zones or the new Docker Hotness or something like Rocket, and it's so difficult to wrap our minds around where is our application code running? How can we manage 10,000 containers that are all running on a single instance? It was so much simpler back in the 70s and 80s when you had one server. It had a name. It had an IP address that the operators had memorized. We don't have that anymore. And the modern data center is just growing in complexity. It's not getting any easier. Furthermore, we have what I like to call the IaaSes, the IaaS, the PaaS, and the CS, which is your infrastructure as a service, your software as a service, et cetera. And how many people here work with multiple operating systems? Nobody works with multiple operating systems? If you have an accounting department, you have Windows, I promise. So the complexity of these tools is exponential. Each time we add a new change, a new factor, a new piece of the puzzle, we increase the complexity of our data center, we increase the complexity of the applications we're running, and how we manage their interoperability. So, again, we're talking about the past now. I swear I'm going to talk about the future. How do we tame this? So what does like the life cycle of the data center look like? So previously, we had what I call the APID cycle, which is the acquisition, provisioning, updating, and destroying of physical machines. So this is like you need to acquire a physical machine from a vendor who sells hardware. You need to take that and put it in a rack in a data center. Someone needs to plug Ethernet cables into it, hook up a power adapter, provision that machine so that it's ready to accept connections or at least be PXE booted into something, and wire it up to the rest of your infrastructure. So to acquire, you would call a vendor, hey, I need this machine, costs $150,000, please to ship it to me within the next 6 to 8 weeks. Cool. Well, then your operators, your DC operations people, they would provision the machine. So they would physically plug the machine in. They would install the initial base operating system, whatever, depending on your organization setup, but there was some step of provisioning. And then there was the life cycle management, which is, okay, we need a new package installed. We need this OpenSSL has another vulnerability. We need to patch it as soon as possible. And that process was manual. It involved an operator like showing credentials, going into the data center, typing things on a console, or potentially doing it over SSH, but originally a lot of this was done like literally in front of the machine. And then when we were done, we needed to destroy that instance, which pre-virtualization meant we needed to wipe the hard drive and reinstall a new base OS. So in terms of time, we're talking weeks to acquire physical hardware. It needs to be made and shipped and arrived and installed. In terms of the actual provisioning, maybe a couple days. If you have a really good sysadmin or DC ops person, maybe 1 day. The update process often took 1 day. Not because it was difficult to update OpenSSL, but because you needed to do it across 500 physical machines, or even 50, and there was 1 or 2 operators. And the destroy process probably took a day as well. Potentially, this is the one that could take maybe an hour or 2. But it's still a painstaking process because very rarely are you going to destroy without provisioning. Otherwise, you just have wasted hardware. So presently, we're in the era of the elastic compute and IaaS era. And they're enabled by one another. So what does elastic compute give us that we didn't have in the past data center? Well, elastic compute kind of helps with the acquisition and destroy stage. So previously, acquisition would take weeks, destroy would take days. With elastic compute, we're talking minutes and seconds. We can spin up an EC2 instance in 45 seconds, even a massive beefy instance, and we can destroy it in seconds. And it's incredibly fast. It allows us to do things like spin up ephemeral infrastructure so that we can run a compute job and then get rid of it when we're done and let someone else use those compute resources. This shifted the cost center from capital expenses to operational expenses. So previously, an organization would need to acquire hundreds of thousands of dollars in infrastructure so that they could run their application. And the end goal for an organization is to make money. So the CapEx is this massive investment just so people could get their applications in the hands of customers, get their web app published, their mobile app ready, whatever it was. Now we're shifting that cost from capital to operational. So we're saying, okay, you don't need the bare metal. We're going to let a cloud provider handle that. We're going to let someone who's providing infrastructure as a service provide you with that bare metal, and they're going to manage the massive $150,000 server bills. They're going to manage the temperatures in the data center. They're going to manage the security of the data center. And they're going to give you an API for you to create virtual machines inside their data center. What that meant was that we needed to put additional money into the operational side of things. We're creating ephemeral infrastructure. That means we need more operations people who have knowledge about how these machines work and interwork with one another in order to manage the scale that we want to grow to. However, the additional operational expenses were significantly lower than the initial capital expenses. Recovering those capital expenses was also very difficult. The rate at which technology grows, as I'm sure many of you know, is drastic. The day you buy a laptop, it is outdated, even Apple, I swear. And people are buying $100,000 servers with 10 gigs of RAM. How many people have more than 10 gigs of RAM on their laptop right now? And this is maybe 10, 15 years ago. The rate at which technology changes is like exponential. It's Moore's law. And let someone else handle those capital expenses. And I think that's where a lot of people are going. And then we have the IaaS era, which is effectively we're letting other people manage parts of our infrastructure. So configuration management came along, things like Chef, Puppet, Ansible, Salt, even just basic bash scripts, and they took the provisioning and updating steps, which would normally take days because an operator needed to type commands into a terminal, down to minutes or even seconds. So we could quickly update a machine by running Chef Client, or quickly provision a machine by running Puppet, or create some type of one-off command by running Puppet apply or Ansible apply. And these configuration management frameworks really changed the way that we think about modern computing. Because no longer did we think about computers as these very static blob-like objects, but instead they were dynamic. They were ever-changing. They were managed in a life cycle type setting as opposed to a physical machine. So we went from days to minutes or even seconds with configuration management, and this opened the proliferation of what I call specialized.com, which is it became really, really easy for companies to offer very, very specialized services to move things out of your data center. So it's really inexpensive to run like an SMTP server, but it's really expensive to do it right. But it turns out that if you create a company that runs SMTP servers and does it right and legally and can sign the emails and do all of the magic that needs to happen, there's a business to be made there. And a lot of organizations recognize that. And they said, wow, people don't want to manage their own SMTP servers. It's easy, but nobody wants to do it. And it's really difficult to get it right. If we get it right, we can make a ton of money. And that's why we see things like SNS, we see things like Mailgun, these services that are offered publicly, some of which are free to a certain tier and some are paid, where you can outsource your email. And just like it's cheaper to outsource certain labor to other countries, it's cheaper to outsource compute work to other organizations that specialize in that type of work. So this is where we see the proliferation of like software as a service and even infrastructure as a service. And that's ultimately what caused all of this complexity. Because no longer do you have one physical machine that is named like Ocular in the corner that the operator knows by name and sometimes caresses at night. That was a joke. Now you have hundreds of thousands of machines running different operating systems. They're running in different virtualized or containerized environments. They're communicating with external services that you have very, very little control over. And as an operator in the modern era, not only are you expected to understand and comprehend this, but you're also required to secure, authenticate, and manage it in the very ever-changing world that we live in. So how can you possibly prevent yourself from doing this? Because there's so many moving pieces, so many moving parts that it's almost impossible for one human being to wrap his or her head around. And the rate at which technology changes, it seems like there's a new JavaScript framework every week. There's always a new provider for something. How can you possibly keep up with any of this? There's an answer. So why did we get here? Like, why do we have containers? Why do we have virtualization? Why do we have servers? Right? Like, it's a question how many people have ever asked themselves, like, why are we using containers? We're using them. How many people here use containers? Yeah, lots of people. Why? Do you actually know why?
Yes.
Well, I know you do. Why?
Why?
Yeah.
Number one, it just solves a package management problem for me. Like, targeting all the Linux distros in the world is just not the game that I want to be in. So containers kind of extract that for me. And then lastly, the absolute abstraction that I need to deploy an application and not talk about Java versus Ruby.
Good. So it solved a problem that you had. So all of the evolutions, all of the iterations that we have on modern infrastructure solved a problem that we had. Virtualization solved a problem of the fact that you need physical hardware to run something, and it's not very ephemeral. Containers solve the problem of not only process isolation, but also distribution, and putting out the flame wars of how you distribute a dynamically typed language to hundreds of thousands of machines effectively and securely. Our original goal was to solve these problems, but we created more in the process. And that's not a bad thing. I'm not saying that with a negative connotation. But it's important to recognize that nobody woke up one morning and was like, it'd be a really good idea to complicate modern infrastructure. But we did. We made it really hard. We made it really hard for new people to join. We made it really hard for operations people to enter the field. You need to have knowledge of like Docker, Rocket, Container, Kubernetes, Terraform, EC2, DigitalOcean, every new cloud player. Have you looked at the job posting for an operations engineer lately? You need a PhD in computer science, infrastructure engineering, Ruby, Python, and everything known to man, because we've made it so complex. And there has to be a better way. So our end goal, and feel free to argue with me on this afterwards, but our end goal for like the past 50 years has always been to effectively deliver and manage applications. Whether that's to another business, if you're B2B, or to the consumer, or whoever, at the end of the day, we're doing all of this. We're on-ramping all of our computing so that we can effectively deliver better applications. Sometimes that's so that we can beat our competitors to market, and sometimes it's so we can be better for our users. But at the end of the day, the end goal is always the same. We want to deliver applications faster, better, harder, stronger, as Kanye said. In other words, we want to move fast and don't break things, which is kind of the subtitle of this talk. Move as fast as you can, breaking as little as possible. And that's hard, because the faster you move, if you take a baseball and you toss it against a window, it's not going to break the window. You take a baseball and you throw it against the window, you're going to shatter the window, your parents are going to be very upset, and you're going to have a bad day. So how can we move fast and not break things? Well, you really can't see that green. Terrible projectors. So if we break the, I'll read it for you, don't worry. So if we break the application lifecycle down into 3 steps, development, deployment, and then maintenance after it's in production. We have development, which needs to be consistent, shareable, readily available, and have as much parity with production as possible. So you want to reduce cost. I'm sure you've all heard talks. The closer your parity of your development environment to your production and staging environment, the more likely you are to find bugs in development. And we know that the cost of finding a bug in development and fixing it is significantly lower than the cost of finding a bug in production and fixing it. There's tons of studies that back that to prove that statement. In the deploy step, we want to start, configure, manage servers. We want to install some packages, potentially install some services, set up some init scripts, et cetera. And then the end goal, all of that is supporting the actual execution of this application. So if this is a Rails app, we want to start passenger. If this is a static binary, we want to execute it or maybe wrap it with something like upstart or systemd so that we can run this application effectively. And that's our deploy process. And that's where a lot of variability happens. That's where the most variability happens. Because everybody develops in the same way, right? They might use Vim, they might use Emacs, they might use Sublime Text, but at the end of the day, everybody's writing code in some language. But how that code gets on the server is where things get a little hairy and drastically differ across organizations. And then the last step is very similar across every organization. It doesn't matter what you're running, Rails app, Django, Java, you want to maintain those. So you need to monitor them, you need to orchestrate them, and then occasionally you need to update them and reconfigure them. Security updates, et cetera. So the application lifecycle is very much broken down into 3 distinct steps. Develop, deploy, and maintain. And are there steps in between? Where does QA fit? Well, that depends on your organization. Does QA fit in the deploy, or do they fit in the maintenance side, right? Do you deploy and then let them QA and then deploy again? Or is QA part of the development lifecycle? They fit there somewhere, but they're not a distinct silo. In fact, you could argue that they're a horizontal bar across this entire organization. So it turns out that we have open source tools for all of those things. And I want to emphasize again that they're open source. So this is not a marketing pitch. You can download all of these things right now. Vagrant, which has been around for many years. How many people know about Vagrant? I have Vagrant stickers. Vagrant is a tool for managing and building virtual machines with things like VirtualBox, which is also free and open source, or VMware, which is not free or open source, but has better performance, I promise. Packer, which is a tool for building for automated machine images. We have Terraform, which is one of our newer tools. 0.4 was just released, which is a way to describe infrastructure as code. I'm going to dive into Terraform here in a little bit. And then on the maintenance side, we have Consul, which is built on top of Surf, which is like service discovery as a first-class citizen, as well as a distributed key value store. And using Consul to maintain and aggregate information across your entire production infrastructure, or staging, or QA. So let's talk about Terraform. So Terraform is a tool for building, managing, destroying, basically managing the life cycle of infrastructure. But it's not just infrastructure. It's not just virtual machines. It's not just cloud instances. It's all of those problems we talked about before. How do you manage the containers versus the fact that you're using a third-party hosted email service? Terraform speaks all of those languages. And if it doesn't speak the language of the provider that you're using, it's pluggable. So you can either write your own and in-house use it, or you can write your own and open source it and let other people benefit from it. So if you're using some one-off email notification service that's just in-house, you can very easily write a Terraform provider for it. And if you're using something that we missed in Terraform Core, you can write a provider for it and bring it into Core and let everyone else in the community benefit from it. So what was Terraform's goal? I think you can see where this is going because we talked about the data center evolution. But Terraform's goal was basically to answer these questions. How do I provision resources, whether those be compute, storage, network, third party? How do I manage the life cycle of those resources? So more so, a little bit embedded in here is how do I manage those life cycle resources in a team? So if Janet creates the instance, but Bob destroys the instance, how do they communicate that? How do they do that without stepping on each other's toes? That's hard. That's a really hard problem. How do I provide a balance between my service providers while also providing core technologies for my data center? So how can I effectively manage my physical brick and mortar data center along with some type of third-party service or any combination of those in between? How do I enforce policy across all of these resources? So Janet can create resources. We already talked about that. Bob tries to destroy a resource, but Bob isn't allowed to destroy resources. How do we enforce that policy? Or how do we enforce the policy that Bob isn't allowed to destroy resources that Janet created? These are real problems that organizations face. They face them every day. And enforcing that policy is very, very difficult. In fact, it's usually done at a managerial level, which is delayed and takes time and just adds additional burden to everyone involved. And finally, how do I automate all of that? Because ain't nobody got time for manual configuration anymore. We learned that from the configuration era. Nobody wants to go SSH into a machine and run apt-get install or yum install anything. We have Chef, we have Puppet, we have Ansible, we have our predefined shell scripts, whatever they are. We don't want to manually configure machines anymore. That's a waste of time, it's a waste of money. So we need to be able to use all of that in here. So Terraform's goal was to provide a single workflow. So it doesn't matter whether you're creating an email service, integrating with a third party, spinning up a Rails app, whatever. It's the same interface, the same workflow, with a unified view. So whether you're an operator, a developer, a manager even, the same view. You see everything the same, with infrastructure as code. And we've heard this buzz phrase a lot, infrastructure as code, infrastructure as code. But Terraform is truly infrastructure as code. It is a text file that shows the representation of your particular infrastructure. And I will show you one in a little bit. It needed to be safely iterated and changed in a team. So this is the team workflow part. But we need to be able to iterate on it. It needs to be versioned. We need to be able to roll back, go forward. It's the thing Git for production, right? Like SVN, Git, SCM for production. How do you git reset -- hard 3 EC2 instances? It needs to be capable of complex end-tier applications, but it needs to be simple enough that anybody can use it. So it needs to be powerful enough that the most experienced and complex problem can be solved, but it needs to be simple enough that any user without any operations experience can pick it up, read a how-to guide, and go. So what does a Terraform configuration file look like? Very simple. If you've used like Nginx, the syntax looks very similar to Nginx. You have the curly braces, the equal sign type thing. You define a resource. So here I'm defining a resource that creates a DigitalOcean droplet. And all of these things are properties like name, size, image, region. And this is basically saying, give me a ½ gig DigitalOcean droplet in San Francisco 1 data center running CentOS 5.8. I don't know why I'm running a 32-bit machine. Don't ask. And I'm going to name it Terraform Web. And then down here, I'm also going to create a DNS record for it, right? Because I can create an instance in DigitalOcean, and it'll have an IP address, but nobody's going to be able to go to sethvargo.com and hit that instance until I create a DNS record for it. And Terraform captures that all in one file. So this is a very, very simple Terraform configuration file that says create example.com and pass in the value of my DigitalOcean's IPv4 address. Or this could be IPv6 address. And at runtime, Terraform is smart enough to build a graph and know that the DNS simple entry is dependent on the DigitalOcean droplet. So it needs to know when it walks the graph, I need to create the DigitalOcean droplet before I can create the DNS record. Because the DNS record depends on data that is only available after I've created my DigitalOcean droplet. Now, in this kind of tiny example, that may not seem like a powerful feature, but when you're managing hundreds or thousands of instances and containers and services, Terraform handles all the interdependency for you. In a way, it's like a dependency solver for the requirements of your infrastructure. And you never have to manually declare anything if you don't want to. As you can see, it's a human-friendly config, or I like to think it's a human-friendly config, although it is JSON compatible for those non-human people. So if you're coming from something like CloudFormation where you're used to writing JSON and you just really want to write your JSON by hand, by all means, you can do that. Terraform will consume that JSON for you. If you're using something that's outputting JSON, like a CI script or some type of third-party tool, Terraform will happily consume that as well. So it's machine-friendly and human-friendly. It's in a SCM VCS format that's friendly as well. So it's very easy if you're using like Git or SVN when you create a pull request. It's very easy to see what lines were changed and what impact that'll have on the infrastructure. So this goes into working in a team and being able to see how changes will iterate over time. But more importantly, it's your entire infrastructure in a single text file, which is truly infrastructure as code. In fact, it's infrastructure as text, because Terraform isn't actually code. It's just a text file. And it's truly the first time where you've ever been able to describe your entire infrastructure as well as their dependencies between as many third-party services and their interdependency as possible in a single file. And you can check this file into version control, and you can run it today, and you can run it 10 years from now, assuming the APIs don't change, and it'll be exactly the same. So it's reproducible, it's repeatable, reproducible, and shareable, which is something that hasn't really been done before. So this is kind of like a revolution in the way that we manage modern infrastructure. Terraform has a graph command. So if you are working with something that's like super complex and you're trying to figure out how is Terraform putting all my stuff together, it'll actually generate a graph format for you. And this is from the previous example. And you can see that it goes from bottom up. So the very last thing that's going to get created is the DNS simple record, because the DNS simple record depends on the DigitalOcean droplet, which depends on various providers, which we'll talk about in a second. So if you read this from the bottom up, that's the order in which things get created. They get created in parallel when possible. So that means you're never wasting time. So if there was a third resource here, maybe like, send an email to someone, right? If that was a third resource and that's not dependent on either of these things, it can run in parallel to both of those operations in a separate routine. So you're minimizing the amount of time it takes to provision infrastructure by parallelizing as much as possible. And Terraform is smart enough and has like an amazing core with graph functions to be able to walk and determine that graph ahead of time so that you don't have to. Because how many people like graph theory? I knew you were going to raise your hand. I like graph theory. It's cool. So like I said a little bit earlier, Terraform is pluggable, and Terraform is pluggable via providers. There are some that are in core, some that other people have written, but providers are just like a plugin to manage some type of service. So like AWS is a provider, right? DigitalOcean is a provider, and they provide resources, but they provide a single integration point for those resources and expose a DSL in the Terraform file that is the same for everyone who uses it. So things like AWS instance, like DNS simple record, these are all things that a provider would provide. And you can write your own in-house provider, you can write your own community provider. It uses a CRUD API, so if you're familiar with like REST or like anything, it has a create, read, update, and destroy lifecycle. You can flag things for destroy. You can taint things, which says like destroy and recreate this on the next run. But basically, it operates the same way like a REST framework works, like create my user, update my user, delete my user. Again, it's pluggable, and it operates in like a layer cake fashion. So this slide's like a little bit confusing, but each provider is kind of a layer. So there's like a provider for managing OpenStack, but then there's also a provider for managing like OpenStack machines. Then there's a provider for managing the containers that run on your OpenStack machines. And since all of this is completely pluggable, you can customize it as much as you want. So if you're running a highly specialized like forked version of OpenStack, you can also run a highly specialized forked version of the Terraform OpenStack provider and support your one-off or edge case features. So it's highly customizable because we don't live in an era where everyone's infrastructure is the same. Because if everyone's infrastructure was exactly the same, then none of us would have jobs because Google would just do it all. And as great as that might be for some people, I like my job. So I'm glad that everything is different, and I'm glad that we have solutions for managing all of these different complex problems. How do you run Terraform? It's simple. It's a CLI, Terraform apply. These are some of the providers that we have right now. So Console, DigitalOcean, DNS Simple, the Googles, that's Google Cloud Platform, not Google Search, Heroku, Mailgun, AWS, Atlas, etc. You can write your own. I think there's a ton more that we're working on. And like when we say AWS, we mean like not just EC2, we mean like the whole AWS platform, and we're working on expanding that provider coverage right now. Terraform is currently in 0.4, so it's very much not beta, but very much not like production either. So there's a lot of changes that are coming, but we like always promise backwards compatibility, and we're always adding new features. Definitely would like welcome your feedback. If you have any questions about Terraform, please come see me afterwards. Terraform Plan is pretty cool because Terraform Apply will like actually go out and execute things. Terraform Plan will query all the APIs and then tell you what it would do. And this is super, super helpful for operators who care about the end state of their infrastructure. So in this example, Terraform Plan is telling me I'm going to create a DigitalOcean droplet named web. It's going to have like some data that you gave me, but then there's these other things that I don't know yet, right? Like I don't know the IPv4 address until after the instance is created, and the DigitalOcean API comes back and says, hey, here's my IP address. You know, the same thing is true in the DNS simple record. We have this kind of like $ squiggly format, which is basically saying I'm referencing the DigitalOcean web IPv4 address. And because that's computed, we also don't know that until after the instance has been returned from DigitalOcean. So Terraform Plan shows you what will happen. It'll explain certain actions. The end goal is to have something like SQL explain for Terraform. We're not quite there yet. What did this look like before? So, wow. How many people managed infrastructure previously? Right? Pretty much everyone managed. You're in the infrastructure track. You probably managed some infrastructure, right? So how many people are using like Chef, Puppet, Ansible, Salt to do all this stuff? Yeah. Okay, how many people are using like shell scripts or manually provisioning servers? Okay, we still got a couple. Cool. It's okay because the future is here. It's here. It's in this room. I swear, the future is here. So there's still a degree of uncertainty because even though Terraform can spin up your instances, Terraform isn't a provisioning framework, right? It's not Chef, it's not Puppet, it's not Ansible, it's not Salt, it's not provisioning the machine. It's creating the EC2 instance and coming back and saying, EC2 is ready. Now what? Right? And it's giving you all of the data to make an intelligent decision of what to do next. Right? So here's the IP address, I'm done, Terraform's done, now what do you want to do? You want to log that? Do you want to like page someone? All of that's up to you. But there's still a lot of uncertainty, especially in the runtime category. Oh, this green is terrible. So let's talk about future ops. So future ops is what I call managing tomorrow's infrastructure, right? So if you look at the visionary companies, like Apple and Google, et cetera, they're not where they are today because they sat at a conference and said, wow, today's technology is really cool. They're where they are today because they sat at a conference and they said, today's technology is really cool. What does it look like 10 years from now, and how can we leverage that to be a successful business? I think we need to do the same thing with ops. So right now, the way ops works is we deploy mutable infrastructure. So we deploy these AMIs, we deploy these web machines in EC2 or DigitalOcean, and then we set up Chef as a service or run a Puppet master, and we push some code, and very, very quickly those machines diverge. They diverge from one another, and they diverge from their original creation. So you're spinning up a base Ubuntu 14.04 instance, and you know what's on it, and then very quickly you don't know what's on it anymore because Chef client ran, and 45 minutes later it's a completely different machine. And this is difficult for operators, it's difficult for security, it's difficult for consistency. So, there's a line there. So with mutable infrastructure, this says confidence, and this says changes. I'm going to trip over one of these wires at some point. And the confidence that you have, so this is initial deploy to 100th iteration. The confidence you have at your initial deploy that you deployed in Ubuntu 14.04 instance is 100%. Maybe 99, right? But you deployed an Ubuntu 14.04 instance. But as you iterate on that, both over time and with various changes, the probability and the confidence that you have that that's the same machine drastically decreases. In fact, that's kind of what we want, right? We don't want an Ubuntu 14.04 instance because you can't just run an Ubuntu 14.04 instance. It doesn't have your application on it. It can't run it. But at the same time, what we have to keep in mind is that the consistency across your infrastructure changes with each iteration. So when your Puppet run fails on 3 of your 1,000 web nodes, they've diverged. They're different, right? They're special snowflakes. You have 3 1,000ths of a special snowflake. And you do that over 6 months, you have 100 1,000ths of special snowflakes. But they're each their own special snowflake because they each diverged at different points in time. And you get your email that's Puppet run failed, and you're like, all right, we'll fix it later. And then all of a sudden, one day, your infrastructure blows up. Or all of a sudden, you're vulnerable to Heartbleed on 3 servers because they never updated OpenSSL. Everyone else did, but those were the 3 Puppet runs that failed 6 months ago, 3 months ago, yesterday. Divergence is a big problem because it removes the faith we have in our infrastructure. It removes our ability to be confident that what we're running in production is consistent. With immutable infrastructure, there's a line at the top, the consistency is always 100%. The production artifact that you deployed and checksummed is 100% guaranteed to be the artifact that it was when you packaged it. We'll talk about what that means in a second. So immutable infrastructure is much faster, right? If you bring up an Ubuntu instance and you run Chef client on it, it takes 45 minutes to download a whole bunch of packages, install a whole bunch of things, potentially restart, write out some users, write out some configuration, and you have to do that for every machine. So it's an operation. You spin up 50 new machines that each take 45 minutes to run. But the process of bringing up that EC2 AMI was 30 seconds, 45 seconds? So what if we could just do all of that beforehand? What if we could just run Chef and get as much done ahead of time as possible? And then when we spin up our AMI, not only is it a production artifact, it's checksummed, it's versioned, we know where it is, we have the consistency, we can spin it up 100 times and it's no different than the 5,000 we spun up before. But at the same time, it's fast. It takes 30 seconds. It's the same AMI. Maybe it takes a minute and a half because you spin up the AMI and then maybe you run Chef like one more time, or maybe you have to wait for your service discovery to kick in. But it's still a lot faster than 45 minutes. Immutable infrastructure allows for greater parity between our development staging, QA, and production environments. If you use the same AMI, and I keep talking about EC2, I do want to clarify, like, these things work outside of EC2. I'm just talking about EC2 because it's what people are most familiar with. If you use the same AMI to spin up something in production as something in staging, that's the same machine. That's a promise that Amazon's EC2 makes. So you don't have to worry about the broken parity. But it would be great if you could give that AMI to a developer too. We'll talk about that in a second. Immutable infrastructure needs automation though, because manually building machines is incredibly painful and nobody wants to do it. So let's talk about Packer. I give Packer the tagline, automated golden images and more. And I know what everyone's thinking, like machine images, golden images, that's terrible. Why are we talking about this? Like, this is the 80s. But this is where I'm asking you to keep an open mind. I'm gonna ask you to throw out everything you know and listen to me for like the next 10 minutes about why golden images are okay. Okay. Why have we generally been against golden images? Well, we've somewhat been brainwashed by marketing organizations of certain companies that convince us that they're bad in order to sell their product. But more so, they were actually bad at one point. Golden images used to be the way in the 80s and the 90s. They were ISOs. They weren't really like VMs at the time. But they changed very, very slowly. They were quarterly, if not like semi-annually. They were blessed. They went through QA. It was like the one image, and it was a big deal to change that image. It was very, very painful for a developer to add a dependency like a system package. Almost impossible. That's a typo. Too long was, tooling. Oh, look at that, yeah. I can read my own handwriting that I typed. The tooling was not as mature as it was today. So building a machine image required somebody to like manually type commands. The same way that configuration management required that someone manually type like commands over SSH. We didn't have tools like vWe and Packer, which can build machine images in an automated way, unattended, without someone sitting there and being like, yes, no, yes, no, yeah, like we have that now. And modern configuration management has changed a lot of how we view machine images. So to put it this way, this is my favorite quote, ops without machine images is like applications without binaries. Because you have absolutely no guarantee that the thing you packaged is the same thing that's running in production. If you compile a static Go binary and you deploy it to production and you checksum it and it matches, that's the thing that you compiled. We can't say the same thing for servers that are running in production, at least not yet. So let's talk about an application lifecycle. You have your source code, you have your binary. When you build your source code, like, you know, there's some libraries that come in here, liba, libb, libc, and if something fails, like liba is updated from 1 to 2 and the API is different, the build fails. You don't have this like half-stale artifact in production. It failed when you build it in CI. But if we talk about the mutable server lifecycle, we have our new server and our like, you know, ready state that we want to get to, but there's so many things in between that can change. Packages, networking, configuration management changes. So what happens if a new package version like comes out? Well, we have a failure. What happens if the network's unreliable and for some reason apt couldn't download the package in the right amount of time? Or the network is reliable but so slow that it takes hours to provision a machine? Or what if configuration management had a bad change checked in and now we have 500 servers that are slightly different and all need to be reprovisioned? Those all lead to failures. But if we look at the machine image lifecycle, all of that happens at build time. So you never have a half a production image. You never have a half configured thing, because if the build passes, it's a production ready artifact. And granted, you can't prevent stupidity, you can't prevent human error, but you can test for that in CI. So imagine you had something like Packer that was a way to automate a build that produced a production AMI And then your CI system, instead of just running tests for your application, actually spun up that AMI, deployed code to it, and that's how you ran your tests. That's 100% parity with production. If you're not going to find a bug there, it's a problem with your test suite, not a problem with your parity. Furthermore, what if you could, actually I'll talk about that in a second, because there's more to come. Packer embraces config management. It transitions the failure from runtime to build time. So there's nothing worse than an email from Puppet or Chef or Ansible or Salt that's like, the run failed, and somebody needs to go SSH into a machine. And anytime you SSH into a machine, you should be asking yourself as an operator, why am I SSHing into a machine? I am about to create a divergence in my infrastructure. That's bad. It's going to cause problems down the line. It enforces parity with staging, but even more so, Packer is able to spit out vagrant boxes. And this is where things get really, really cool. So not only can you produce an AMI that can be used in production, but in the same Packer run, you can produce a vagrant box that can be distributed to your developers that is 100% parity with that AMI that's running in production. They run vagrant up, and they have the production infrastructure on their local laptop. And you're not paying EC2 an extra $10,000 a month for them to run their own staging instances. It's going to save you time, it's going to save you money, and it's an automated process. So what does the future look like? Well, I made this handy infographic for you. It's interactive. So there's an operator, and he's at his computer. And he makes some changes to some CM, because the future isn't without CM. Like, configuration management isn't dead, but it's a solved problem, right? Like, there's players in the market. We've solved the problem. There's going to be improvements, but it's a solved problem. So we should use those tools, because they're very good at what they do. So we make a CM change to our Chef or our Puppet, and we create a new Packer build. Well, Packer is going to spit out an EC2 AMI or a DigitalOcean droplet or some type of production artifact that's deployable. But it's also going to spit out a vagrant image. And then our developers are going to pull down that code onto their local laptop. And they're going to vagrant up. And they're going to develop, and they're going to write code against what's deployed in production. So that whenever the developer has 100% parity with production and they deploy, the probability that there's some type of weird thing going on where worked in dev, ops problem now, I almost put that meme up, but I didn't, it's eliminated. Or I guess eliminated is a strong word, but it's drastically reduced, which ultimately saves the headache of operators and the money of managers. It makes everyone happy. So there's one last question we have to answer. And that's like, once this thing's in production, what do you do with it? And there's another open source tool called Console to manage that. So when you have 10,000 machines, whether they're Docker containers or VMs or physical machines, and you're treating them like production artifacts and they're immutable, how do you get them to talk to one another? Because you can't hard code the database.yaml of your Rails app, because that changes whenever the rest of the infrastructure changes. And how do you figure that out? So we wrote a tool called Console to figure that out. Console is first-class service discovery, and it uses a number of ways to do that, the most popular of which is the DNS interface. So you just point your Rails app at postgres.mycompany.console. And Console not only handles the load balancing between all of those instances with various strategies, but you don't need to worry about IP addresses, you don't need to worry about anything. You just tell Rails, this is where the database server lives, and Rails doesn't care. Console also has built-in health checks and service checks. So there's node level checks and service level checks. So a service is something like Redis. A node is something like 1.2.3.4, a physical or virtual machine. A node level check is something like memory, like holy crap, I'm at 100% utilization, or 100% CPU utilization. I'm in swap, 75% swap right now. And then service level checks are like, there's only 2 Redis nodes available, and you told me you wanted 5 at all times. And these checks can fire off a number of basically external reactions, things like sending an email, things like sending a text message, doing nothing, just logging it, etc. The nice thing is that these service level checks correspond directly to the service discovery. So if you have a database server that is unhappy, it is 100% CPU usage, 100% memory utilization, its health checks start failing, Console will take it out of the pool. Meaning when someone hits my database, postgres.mycompany.console, no more traffic goes to that unhealthy host. And it's immediate, or as immediate as you can have in a distributed infrastructure. And it goes the other way too. When that service becomes healthy, it gets added to the pool. So it also goes to say that when a new service gets added, if you auto-scale your database instances and all of a sudden you have 3 more, as soon as those nodes report to console, they become available in the pool. And your application never needs to change. It's first-class service discovery built into monitoring. And it's awesome. Last but not least, console has a distributed key value store, an HA distributed key value store. This is great for managing things like feature flags. Combined with tools like console template and env console, an operator or a developer can change one flag in console and completely change what is deployed in production, or the flag that's turned on or off, or the version of an application that is deployed. Or you can just store some straight up key value data. Please don't use it like Redis. It's not Redis. So how does console work? What does it look like under the hood? You'll have to find me afterwards and ask me. Any questions?
How do you answer the infrastructure teams? I only want to have 4 AMIs. I don't want to have to manage 1,000 AMIs.
Okay, so the question is, the infrastructure team doesn't want to manage 1,000 AMIs. They only want, 2 or 3 that they can keep their head around. You don't. I think the corollary there is that's like a developer saying, I only want to manage 3 Git SHAs. I think on the surface it makes sense, but you're not managing these AMIs anymore either. It's no longer a manual process. Packer's going to generate it. It's going to output the AMI ID, and that gets stored in like some type of registry or something. And people are like, all right, this is the latest, front-end web app AMI ID. So you're not managing them anymore, right? So as an operator or like the infrastructure team, they're not worried about which AMI is doing what. They're concerned with like the latest AMI. Just like Git is concerned with the latest head commit. And if you want to reset to a previous version, you have all of that history, but you're really only concerned with like master and maybe like another branch at any time. Does that make sense? Yep. Or wait.
Can you share how to integrate console with configuration management tools? So like using Chef, you can do a Chef search to dynamically discover things in your Chef environment. How might that work with console?
So an interesting thing with like the way Chef search works is it requires the node to be registered and reported back to the Chef server. So trying to use Chef search as service discovery is actually probably not a good idea. Because it's not nearly as real time as something like console. So when people ask this question, what I usually challenge people to do is instead of using Chef as like a registry for service discovery, use Chef for what it's really good at, which is provisioning nodes, and have Chef install the console agent. And you can also have Chef drop off console templates, which is kind of meta, but you can keep your console templates in your templates directory in Chef. And you can have Chef write out those templates, and you can have Chef start the console template process, which is going to watch console for changes and dynamically write out a template on disk for you. It's kind of like etcd if you've used etcd. If you're putting a lot of work on the Chef server by using Chef for service discovery, you're running Chef like every 15 to 30 minutes, which means your data is always 15 to 30 minutes stale. Console uses a pull push model, so it's always as real time as possible. As soon as the data like happens, it's pushed out, and like all the agents know, and the console infrastructure knows. So you're gonna get a more real-time reaction, pushing the service discovery into something like console, or even like a different service discovery tool that's not console, as opposed to using something like Chef for service discovery. But you can really leverage like Chef or Puppet or Ansible or Salt for what they're really good at, which is like the actual configuration management side of things, and then leave the discovery up to another tool that really focuses on that.
Hi, I have a Terraform question.
Okay.
So how do you deal with, you set up your plan, declare that this is my plan. How do you execute the same plan against multiple regions?
So Terraform
I
0.
asked the question because I've looked at it, I've used it, and that's one of the missing pieces for me, I think.
So the easiest answer, which is not the most UX friendly, is you make the region a variable, and then you specify the region as a variable on the command line with the -var flag. So you say that the region that I want this to spin up is like -AWS region. I think it's a default flag. And then you run Terraform plan -region SFO1 or US East 1, sorry, wrong cloud provider. You run your apply, and then you do that again running with like, -US West 2. What you have to be careful for is the output file that Terraform is going to generate for state is going to overwrite it. So you'll need to also specify the out parameter when you specify a different region, because it's going to try to, by default it uses the TF state file. So it's going to try to write over that file, and it's also going to tell you that everything has changed, because it's going to compare its local state with the remote state, and none of these things exist in US West 1 because you only created them in US East 2. So you need to specify the out parameter to keep that separate.
A follow-up question, if I can. So the state, the thing you get back once you execute the plan, how does Terraform use it?
Not sure I know what you're asking.
I mean, they stores it somewhere, so does it make use of it after the fact?
Yes. So Terraform needs that state file to know various things that either aren't exposed via an API or dependency ordering things that can't be calculated afterwards. So if you delete your Terraform state file, Terraform is going to think that the diff between your local machine and the production infrastructure is 100%. They're completely different, because your local state says nothing is created, but when it queries EC2, it's going to see, holy crap, there's 100 instances here, and it's going to mark them all as tainted, and it's going to destroy them and recreate them. So there's two, kind of like predicting your follow-up question. Yes, you should check it into SCM if you're working in a team or not working in a team, or you can use Terraform 0.4 shipped with remote state, which is where Terraform will automatically upload that remote state to something like an S3 bucket or Atlas or like a network share that you specify, and your whole team needs to have access to that remote state, and it'll actually manage the updates to that remote state.
Thank you.
I think there's one up front.
Hi, first of all, great talk. My question was that how is using Terraform different than running masterless Puppet, given that Puppet has a similar DSL and it has the notion of dependency graph? So I was just wondering, like you said, it was sort of like the first time like it was possible to say configuration of IaaS providers in a friendly DSL kind of a thing, but I was just wondering what is the difference there?
So I think like Puppet and Chef, I haven't seen it from the Ansible side yet. They're both trying to enter the infrastructure provisioning space. As far as like the depth graph question, I think the biggest win Terraform has there is it can be highly parallelized. So the amount of execution time is significantly lower. I think, I think potentially configuration management should focus on configuration management, because they're very good at what they do. Like Chef and Puppet and Ansible, like they're very good at configuration management, and there's still a lot of problems to be solved there. And I think other tools like CloudFormation and Terraform are really, really good at provisioning infrastructure. And potentially they run the risk of like running themselves thin by focusing on things that are a bit outside of the domain of traditional configuration management. And I've been working with like Go a lot lately, and part of the Go paradigm is like small, kind of like microservices, like isolated things all talking together as opposed to like one monolithic thing. And I think like that model works really well, where like configuration management is very well defined, and like infrastructure management is kind of its own thing. So I think the biggest difference is on the negative side, you have another tool you have to learn, right? Like you have to learn Terraform, you have to learn the Terraform syntax. I think one of the positives is that it's developer friendly, it's highly parallelized, and it's like specifically the goal. There's like much broader support for a much different, like a much broader number of providers.
So my question's about Terraform in itself, and just a question, you were talking about accessibility for like new developers into the field of like whether it's SysOps or DevOps or something like that. in your experience or so far, is the goal of Terraform to make it more accessible, and does it make it so that like someone new doesn't have to learn basically CloudFormation and then learn Terraform in order to actually leverage Terraform?
That's certainly one of the goals. I wouldn't say that that's like the one goal. I think the big picture goal of Terraform is to have one text file that describes your whole infrastructure. And then kind of like the secondary goals around that are it needs to have a super powerful UX, both on the command line and the output that comes back, so that newbies and like people who are new to the organization or the company or the tool can pick it up and run with it. It needs to be powerful enough that the people who are experienced can also specify 5,000 command line flags and tune it the way they want. I think like one of the goals is definitely that anybody should be able to pick this up and run with it. And the how to good kind of really really goes with that. It's like, here's 5 lines of code, 2 of which are curly braces. Like, go spin up a DigitalOcean droplet by running this one command. Any other questions? Cool. Thank you everyone for coming.